All right, so we're going to move on to chapter 3 then. All right, water and life. And this chapter is mostly about water. Okay, such an important substance biologically. So there's our planet, sometimes called the blue planet because of all the water that's on it. An enormous amount of our surface, the surface of the planet, is covered in water. Can be covered in ice, still water, be covered in liquid water, and there's water vapor in the atmosphere. All right, lots and lots of water. So on planet Earth, we've got ice, which is water, just frozen. We've got liquid water, obviously water in its liquid form, and we've got water vapor. Can you always see water vapor? No. In fact, there's water vapor all around you. All right? When you see the clouds, that's kind of water vapor that's become condensed out as tiny little water droplets. All right? So there's water vapor all around you. You breathe out water vapor, lots of it. You can't see it. On a cold morning, you can see it because that water vapor condenses out when it hits the cold air and forms tiny little droplets, which is what you can see. Okay? All right. Okay, so concept 1 then. I want to talk about hydrogen bonding and the properties of water and how hydrogen bonding is responsible for many of the properties of water. And remember, you've got to understand polar covalent bonds. I'll go over hydrogen bonding a little bit again, but hopefully you remember most of that. So, the properties of water then. The unique properties of water largely result from hydrogen bonding. So here we've got a water molecule in the middle. There's a hydrogen bond with the water molecule on top between the hydrogen and the oxygen. And that water molecule can form a total of 4 hydrogen bonds. So each water molecule can form 4 hydrogen bonds with other water molecules. And those hydrogen bonds are made and broken all the time. They're transient. They're not permanent in this state. So of course, if this hydrogen bond breaks up here, then it can simply make another hydrogen bond with another available water molecule. Okay?
The atoms that make up a water molecule are in a constant tug-of-war over their shared electrons. Oxygen exerts a far stronger pull on the shared electrons than does hydrogen, and so the electrons spend more of their time closer to the oxygen atom. Because of this unequal sharing of electrons, the oxygen atom in a water molecule actually has a slight negative charge, and each hydrogen atom has a slight positive charge, even though the water molecule as a whole is neutral. Because of the unequal sharing of electrons and the resulting positive and negative poles, a water molecule is said to be polar. The polarity of water molecules causes them to be attracted to each other. Since the positively charged atom involved in this special type of attraction is always a hydrogen atom, this kind of bond between molecules is called a hydrogen bond. Each water molecule can hydrogen bond to 4 other water molecules. A hydrogen bond is weak and lasts only a tiny fraction of a second, but it takes a lot of energy to overcome the combined attraction of many hydrogen bonds. This explains water's great capacity to store heat, its high boiling point, surface tension, and several other unusual properties.
Good? Did that help? I think it does. I always love to see the movie, yell at animation. Okay, so the unique properties of water then are a result of hydrogen bonding between water molecules. So let's have a look at more depth at some of those unique properties of water. The first 2 I want to look at are cohesion and adhesion. What does cohesion mean when we talk about water molecules? They want to stick together. They're cohesive. And what do we mean by adhesion? They like to stick to other things. Not everything, not all other things, but they like to stick to a lot of other things. Yep, they're adhesive. Good. So, water molecules like to stick together. That gives them cohesion, and they stick together because of hydrogen bonding. And they like to stick to other things. That we call adhesion. They like to stick to other things because they are polar molecules, and if there's any opposite charge around, then they like to stick to it. So do water molecules like to stick to everything else? What about if I had something that had no polarity? A non-polar substance? No, because it's the stickiness, the adhesion is a result of opposite charges attracting. Water has positive and negative charges on the water molecule, and so if there's something that's negatively charged around, then that positive charge will be attracted to it. If there's something negatively charged around, hang on, did I get that the right way around? You know what I mean. But if there's something that has no charge, then those positive and negative charges are not attracted to it, they won't stick. Good? Okay. So, let's have a look at an application of that then. Think about trees, especially really tall trees. The water has to get from the soil into the roots, and then it's got to travel to where?
To the top of the tree.
To the leaves, all right? It's one of the main places where water's used. You're going to find water throughout a plant, but one of the journeys it makes is from the soil into the roots. It's got to go up the stems, it makes its way into the leaves. That's a tough journey for it to make. And big trees can use and lose a lot of water each day. Let's take a big oak tree on a normal summer's day in England. It can lose more than 80 gallons of water in a day through its leaves as water vapour.
What?
Yes. Amazing but true.
How much is it taken up in a day then if it loses that much?
So it loses a lot more than it actually uses in photosynthesis. All right? So think about this, a big tree. If you had to carry 80 gallons of water to the top of a tree, that requires a lot of energy, doesn't it? So let's see how plants do it. All right, so here's those first trees I showed were conifers, probably in the Pacific Northwest somewhere of the United States. These are eucalyptus trees. I don't know, they could be Australia or Canada, California. There's an awful lot of eucalyptus trees. But they are tall trees. Many of them exceed 300 feet in height, and they've got to pump a lot of water, or they've got to move a lot of water to the tree tops. If you took a cross-section of a tree, twig, or branch, it would look something like this. And you can see these look like little cross-sections of tubes. So in the wood of a plant, you've got lots of almost microscopic tubes called the vascular system of the plant. Now, the part of the vascular system in the plant that's responsible for moving water is called the xylem, or xylem vessels. And xylem vessels typically move water from the roots up to the leaves. There's another system of plumbing inside the plants called the phloem vessels, and the phloem moves photosynthates, that's sugary substances produced in the leaves to other parts of the tree. So let's concentrate on the xylem though, which moves water primarily from the roots to the leaves. So I'm going to show you an animation as how it happens. But I want you to think about this. Here's our awesome big tree. All right? And up here we've got a leaf. Now, from that leaf, you're going to lose water as water vapor. So water molecules are continually leaving the leaf through little pores called stomata. You can't see it, it's just like you can't see the water vapor in your breath. But that water molecule, just before it goes into a gas, before it leaves as a little water molecule in the water vapor, what is it hydrogen bonded to? What is that water molecule hydrogen bonded to?
The xylem vessel?
What are water molecules hydrogen bonded to?
Other water molecules.
Other water molecules, right. So that water molecule is hydrogen bonded to another,
Water molecule.
which is hydrogen bonded to another, which is hydrogen bonded to another. All right, now we can keep going down. You can almost think about a big long column.
So the hydrogen bond is what it's using to connect to get the water up the tree.
So if you kind of think about this, as one molecule leaves, it kind of pulls the rest of them up. It's not quite like that. It's not quite as simple as that. But does that make sense? Yep. All right. It's a bit like this. If we all held hands, big long chain of us out into the hallway, right? And I wanted to go out that door. I would tug and then leave. Pulls you all along. Okay? Not quite that simple, but this animation will help.
How does water get from the roots of a tree to its leaves? The evaporation of water from leaves moves water molecules up from the roots. The evaporation exerts a pull that is relayed downward along a string of water molecules from leaf to root. Hydrogen bonds cause water molecules to stick together, a phenomenon called cohesion. As each water molecule evaporates, it pulls on the next water molecule, and it pulls on the next. This relays the pull of evaporating water molecules all the way down to the roots. The cohesion of water helps to keep gravity from pulling the water molecules back down.
Good? That is a bit more complicated than that, and I want to fill you in. So this movie is actually awesome.
Trees must transport water and minerals to their highest leaves. How does this happen? Interestingly, trees move water by losing water. Evaporation of water from plants is called transpiration. Water diffuses from inside a leaf to the outside air through pores. Inside a leaf are air spaces. Water evaporates constantly from the surfaces of surrounding cells. To better see the water, let's show it in blue. Notice that water forms a film on cell walls, including the walls of cells in leaf veins. Within the veins are hollow, tube-like cells, shown in brown. These cells, also found in stems and roots, are part of a tissue called xylem. Water and minerals are transported from roots to veins through the xylem, and then from veins into the walls of other leaf cells. What maintains this flow? Let's look at the surface of a plant cell. A thin layer of water covers the cell wall. As water evaporates, the cell wall begins to dry out. Look at how water sticks to the cell wall. This is called adhesion. Water molecules also stick to each other. This is called cohesion. Cohesion and adhesion are the results of hydrogen bonds, the dashed lines. Because of cohesion and adhesion, transpiration creates a tension from leaf cells through the xylem to the roots that pulls water molecules up the plant. Now let's look at how water and minerals enter through the roots. Roots are highly branched, creating a lot of area for absorption. Root hairs near each root tip increase the surface area. Water and minerals, shown in yellow, can follow two paths from cell to cell within a root. In one path, they travel in the cytoplasm, which is connected between cells. In the other path, they travel within cell walls. In the path within cell walls, however, they encounter a waxy barrier that blocks entry to the xylem. To continue, the water and minerals must cross a plasma membrane. In this way, only certain minerals can enter the xylem. After moving into the xylem, water and minerals are pulled up to the leaves. Water evaporates from leaf cells into the air spaces inside leaves and exits through pores. And that's how water can reach the highest leaves of a tree.
Good? It's interesting, isn't it? All right, so water has cohesion and adhesion. So anybody know what this guy is? It's a water bug. It is.
Something spider?
It's called a water strider. It's an
Strider.
insect. All right? It is an insect. And these are really cool, actually. You'll see them on water bodies, and they seem to skate around on the water surface. Now, their legs have these very hydrophobic hairs on them. Hydrophobic means water hating. If you've got a phobia, you don't like it. Hydro, water, phobic. Hydrophobic hairs. Don't like water. Primarily because they've got a lot of non-polar waxes on them. all right? And they're sort of hairy, gives them a big surface area. And the water molecules like to stick to each other. So that surface tension can hold up this little insect. Now these are actually pretty cool. Does anybody know what they do hanging out on the water surface while they're there?
Do they eat crap on the surface? Stuff on the surface?
They do eat other things on the surface, yeah. So what they do, they're actually voracious predators. They'll hang around on the surface, they'll feel vibrations on the water.
Oh no.
And the minute another insect or something else that's small sort of crashes into the water and gets stranded on the surface and starts to shake
So
its
the
legs and its
water's like a
wings.
big web.
Sorry?
So the water's like a big web for him.
It can sense, yeah. So it senses that distress and it zooms over and it's got a big mouth part called a stylet, which is like a hypodermic needle that runs almost the length of its body underneath. And it moves that out, jams it into the victim, sucks its juices till it's dead. Very cool. I remember as a kid playing with these on my parents' pond. They've lived in the same house for, I don't know, years, and they have a pond in the backyard, and it used to be a World War II air raid shelter. And there were these pond skaters on there, and I used to just fool around with them as a kid, and I couldn't understand why they floated. So I used to then, put a cup over them and try to sink them, and they would always come up to the top and float again. I felt kind of mean, but it was really fascinating doing it. They always used to float to the top. All right. And of course, many organisms, this happens to be a spider, make use of that surface tension, and that's where they live, on the surface of the water. Okay? All right. Okay, you good with cohesion and adhesion then? So concept number 3 is the relationship between density and temperature for water. First, I want to make sure you're okay with density. It should be a concept you're okay with. So in this case, we're going to talk about literally the number of particles. Now that could be molecules or atoms. In our case, and with water, we're going to talk about the number of molecules. The number of molecules per unit volume. Okay? So I could give you, for example, exactly 1 litre of water in a beaker, exactly 1 litre. The density would be the number of water molecules in that 1 litre. Okay? Now, as I change the temperature, the density changes a little bit. You'll either get more water molecules in a litre or fewer water molecules in a litre. So think about this with air in a balloon, right? Try this at home. Get a balloon, blow it up. Tie a knot in it. And you can see how big the balloon is. There's a certain density of air molecules in the balloon. Then put it in the fridge. It's going to make it go cold, right? And you're going to watch that balloon shrink a little bit. Has the number of air molecules inside changed? No. They just get more close together. The density has increased, right? Let's just say that balloon had a volume of 1 litre, and let's just say we had 1,000 air molecules in that balloon. It's more than that. When you put it in the fridge, our volume goes down, right? So we did have 1,000 per litre. Yep. When we put it in the fridge, the volume goes down. Let's just say the volume went down to 0.5 litres. Yeah? And we still had our 1,000. Now we've got 1,000 in half a litre, which is the same as 2,000 per litre. Is everyone okay with that density? Now what you can do with your balloon also, take it out of the fridge, get it to room temperature, and then put it in a windowsill or in the sun, and you'll watch it get bigger. Okay? The air inside expands, and that will reduce its density. Okay? So the density we're looking at then is number of particles, in this case molecules, in a certain volume, in a certain amount of space. Good? Okay. All right, so water then is one of the few substances, common substances that is, that's present in our environment in all 3 states, liquid, solid and gas. And I kind of like this picture. So you've got the liquid water, underneath the solid ice, and there's water vapor everywhere. Okay? There aren't that many other substances that are common that have all three states present like that. Here's another picture. Here you've got some swans, and there on liquid water you can see all the water vapor, little droplets, a lot of it is around them, and you've got ice in the background. Okay, I think this picture is from Japan. I wish I had a picture of those monkeys. You know the monkeys that are in the hot springs in Japan? You seen those pictures? They're awesome. I'd love to go see that. Because they're in the warm water, there's water vapor everywhere, and there's snow and ice on the banks. All right, so here's a curious thing then. We can take a glass of water, we can dunk in an ice cube, and the ice cube floats. So what can you say about the density of ice relative to the density of water? The ice is less dense. Water is one of the few substances where the solid is less dense than the liquid, and as a result, it floats. That's really important ecologically, the biology of lakes and rivers and streams and so on. It means you can do this if you live in a place like this, right, where the lakes freeze over, you've got a dog and some ice skates. So water then is at its most dense at 4 degrees Celsius. Now, that's about the temperature of most of your refrigerators. Most of your refrigerators are set to a temperature of about 3 or 4 degrees Celsius. At that temperature, water is at its most dense. And water is at its least dense at 0 degrees Celsius. That's freezing point. That's a tiny little difference, you're right. Not much of a difference in temperature, but it is in density. All right, so I want you to think about a frozen lake. Frozen lake. There's our frozen lake. There's our ice on top. I want you to label the temperatures in that lake. I want you to label the temperature there, the temperature there, and the temperature there. Label each of those 3 temperatures in the lake based on what you know. You should be able to work this out. What temperature is the ice? 0. Or, I'm going to put 0 degrees Celsius. Because ice freezes. No. What did you say? 32? 32 what?
I didn't say anything like that.
I don't even understand what this Fahrenheit business is. Okay. All right. 0 degrees Celsius. That's the freezing point of water. Now, honestly, if it's a really cold place and it's negative 20 degrees up here, chances are the ice is going to be colder than 0 degrees Celsius. Is everyone okay with that? Your freezer at home is about negative 20 degrees Celsius. What temperature is the ice in your freezer? Negative 20 degrees Celsius. It just so happens water freezes at about 0 degrees Celsius. That's when it starts to freeze. But put it in a place where it's negative 20, it will get to negative 20. Good? All right, so let's just say the ice is at 0. All right? What do we know about the water at the bottom? Not temperature-wise, density-wise. It's the most dense because it's the stuff that's going to sink. And water is its most dense at what temperature? 4 degrees Celsius. Now, it's possible that all the water's at 4 degrees Celsius, all right? Or sometimes it can stratify. Sometimes it might be 1 degree, 2 degree, 3 degree, and then 4 degree at the bottom. All right? might stratify like that. So where's the warmest place in frozen lake?
Bottom.
Right at the bottom. That's it. It's not much warmer, let me tell you. All right. Okay. So the fact that ice is its least dense at 0 degrees Celsius, if that wasn't the case, what would happen to a lake? Would it freeze from the top down? It might freeze from the bottom up. All right? So that's a very important property. It means that lakes, when it gets really cold, I mean, they can completely freeze, right, if it gets cold enough, but it means that ice will form on top first. That, to some degree, can insulate the water below. But it means you can have liquid waters below where organisms can live, not just one big solid mass. Yeah? Okay. All right. So, look at this guy. He's quite happy in the very, very, very cold. All right. There we've got some ice on top. Water molecules. Ice obviously is frozen water. The water molecules are held together by hydrogen bonds. When we reduce the temperature that much, the hydrogen bonding tends to become very regular, patterned, and structured. And as a result, the water molecules in ice are slightly further apart than what they are as a liquid. And that's what makes it slightly less dense. Okay? All right. In liquid form, on the other hand, the hydrogen bonds are continually being made and broken, and the water molecules just ever so slightly closer together, and that makes it more dense. Okay. So, just to sort of cap it out with lakes, it's one reason why you can get some stratification in lakes. Right? So you must have been swimming in a lake and there's that nice warm layer of water up top, and all of a sudden you hit a very cold layer and it seems to be really cold down below. So lakes can have this stratification, and it has to do with the layering of water because of its density at different temperatures. Okay? The cold stuff, the 4-degree water, is going to sink to the bottom, always. The warm stuff is going to float on top.
Except when it's freezing.
Right, when it's freezing though, well, the warmer water is going to, yeah. Well, the 4 degrees Celsius water is always going to sink down the bottom. That's when water's at its most dense. At 0 degrees, it's going to be on top. This is an example of a lake that's not frozen. It's just a cold lake. All right? The 4 degrees Celsius water is going to sink to the bottom. There's no ice around. It's not super cold. In fact, the sun's shining in this case. So you're going to get warm water. So you're going to get warm water at top. Well, this same frozen lake, in the summer, the ice is going to melt. That top water is going to get warm, but the most dense water will always be down the bottom. So the temperature, as long as it stays cold, is always going to be 4 degrees Celsius at the bottom. Okay? If it's a deep lake and the water stays cold. Good? All right. Okay, so now I want to look at water as the solvent of life. All right? Water is the solvent inside and outside of your cells. So I want you to become familiar with these terms. First one is what a solution is. A solution. We'll use it time and time again in lab. So a solution then is a liquid that's a completely homogeneous mixture of different substances. You can think of homogeneous as being sort of uniformly spread around. So if I take a beaker of water and I drop in some ink, initially the ink might kind of sink to the bottom and just form like a little, puddle of ink at the bottom. That wouldn't be a solution. If I mix it completely so the ink is uniformly distributed throughout the water, then we'd have a solution. Now I'm assuming the ink is a substance that dissolves and not little particles that just float around. So there's a difference between a substance that dissolves in water and just tiny little particles that are suspended in water. All right? Okay, so a solution, homogeneous mixture of more than one substance. Okay? Solvent, then. A solvent is the dissolving agent for the solution. Typically it's a liquid, and stuff dissolves into that liquid. And it can be a variety of things. I think gases can dissolve into water.
Yeah.
Yep. Are there liquids that can dissolve into water? Yep. Are there solids that can dissolve into water? Yeah. Lots of things dissolve into water. So water in that case is the solvent. And then we've got the solute. And the solute is the substance that gets dissolved. I do want you to carefully make the distinction between a substance that is in suspension versus a substance that is dissolved and in solution. If I get some sodium chloride, table salt, and put it in water, it dissolves. And I'll show you how that happens in a moment. But the sodium and chloride ions that are held together by ionic bonds, they literally get ripped from the lattice, and you've got individual sodium and chloride ions that get surrounded by water, and they're uniformly distributed in the water when it dissolves. If I take a very, 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 very ultra-fine powder like cornstarch, okay, I can add cornstarch to water. You know what cornstarch looks like, right? I can mix it up, and it looks like it's uniform. It even appears like it's dissolved, but it's not. Those tiny little particles are in suspension. They're just floating around. They're not dissolved, okay? I can take very, 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 very fine sand or dust, put that in water and shake it around, and it just goes in suspension. It's not soluble, it doesn't dissolve. Is everyone okay with that? If it doesn't dissolve, it doesn't form a solution. It's not part of the solution. Okay. So an aqueous solution, then, is a solution where water is the solvent. We can have solutions where water isn't the solvent. Sometimes ethanol is our solvent. Sometimes hexane can be our solvent. So we can have solvents that aren't water. But in your body, water is your solvent. Everybody okay with those terms then? Solution, solute, solvent, and aqueous solution. So when we put sodium chloride then in a beaker with some water, here's kind of what happens. So over here, you've got the sodium chloride, and you can see the green ones are the chloride ions, and the little yellow ones are the sodium ions. They're held together by ionic bonds in this sort of regular lattice. Okay? As soon as we add it to water, what happens is the polarity on the water molecule adheres to those ions, and it literally rips them away from the lattice. So here's a little sodium ion. Eventually, that's positively charged. The negative sides of a water molecule are going to come close to it, and the attraction for the water is going to be greater for that sodium ion than what the attraction is to the other chlorines. And it's going to pull it away, and then the sodiums are going to get surrounded by water molecules, obviously the oxygen, which is the negative side in, and the chloride ions are going to get surrounded by water also, but the hydrogen side in, the positive side in. Good? So, water is a really good solute for ionic compounds held together with ionic bonds. Okay. Water, though, can also dissolve many other substances. So here's an example. This is a whole molecule. In this case, it's a protein. Proteins in your body tend to be huge molecules, enormous molecules. They're very complex. We're going to look at the structure of proteins later. So proteins are really big molecules. Proteins that have polar parts to them or ionic regions to them. Then they can dissolve in water also. Substances that have no ionic or no polar parts won't dissolve in water. Like oil. Oil doesn't dissolve in water. There are no polar parts or ionic parts to most oils, and they don't mix or dissolve in water. Good?
So that's why you can't put like a grease fire out with water, because they don't mix.
Right, they don't mix, and the oil, the grease, will float above the water. All right, so the way water puts out a fire very often is it cuts off the oxygen supply. But with a grease fire, of course, the grease is just going to sit on top of the water and doesn't do a very good job of cutting out the oxygen. And I think at those temperatures, I think what can happen is water can actually get disassociated into hydrogen and oxygen, and that sort of adds fuel to the flames, literally, I think. Okay, so a couple more terms for you then. A hydrophilic substance. Let's break the word down. Hydro refers to water, and philic means loving. Hydrophilic means water loving. So a hydrophilic substance is one that has an affinity for water. It likes water. And what would be the opposite of a hydrophilic substance? Hydrophobic substance. Good. Hydrophobic substance. Doesn't have an affinity for water. Think about that as water hating. Hate is such a strong word, though. So oil molecules then, all right, they're hydrophobic, water hating. They don't have any polar parts to them. They're dominated by non-polar bonds, and as a result, they don't mix with water. There's nothing in an oil molecule, really, that a water molecule can be attracted to. There's no polarity. Is everyone okay with that concept? Yeah.
Oh, is hydrophobic and hydrophilic like the reasons why, like, you see on YouTube sometimes people put like mercury in the water and it explodes or something like that? Is that because of this? It doesn't like the water?
No, I've never seen mercury
Or, like,
explode.
It could have been something else.
If you put
Like
potassium,
phosphorus or potassium.
if you put a little cube of potassium in water, then you get a reaction which is so violent, then it explodes. It's just a very, very violent chemical reaction. Okay? Yeah.
What are the elements of oil?
So oil is primarily made up of carbon and hydrogen. Sometimes a little bit of oxygen in there as well. But it's primarily hydrogen, carbon. Sometimes some oxygen. Okay? Well, there is oxygen, just not much of it. It's almost all carbon and hydrogen. Lots of carbon-hydrogen bonds and then non-polar bonds. Okay. So think about a cell membrane. Cell membrane is made of chemicals that are very closely related to oils. They're called phospholipids, right? And they have, most of the phospholipid molecule is hydrophobic. And they do have a tiny little hydrophilic region to them. All right. So you've got this cell membrane, which is the envelope that surrounds a cell, and one of its primary components is hydrophobic, doesn't mix with water. Water's inside the cell, water's outside the cell. That's pretty handy, isn't it? That's a pretty good idea, right? It's like you wouldn't make a Ziploc bag to hold water out of, I don't know, something that water's going to dissolve in, would you? It'd just disappear, right? Okay. All right, now we're going to get on to this last concept, concept 4, and it's the concept of pH, acids, and bases. Right, got to think hard for this one. So I want you to think about two water molecules. There we go, 2 water molecules that are hydrogen bonded to each other. Is everybody okay with this? 2 water molecules, hydrogen bonded to each other, yeah? So here's what can happen. It happens very quickly and I guess statistically very rarely. But in a beaker of water, you've got many water molecules. So even though it's a rare event, it's going to happen quite often because you've got so much water. But here's what happens, is one of these water molecules is going to disassociate. Okay? It's going to disassociate. Here's what I mean by that. I can take an H2O, okay, and I can break it apart. I can break it apart into a hydrogen and an OH. Is everyone okay with that? In fact, we can just apply it to our chemical equations, can't we? Here we've got a water molecule, 2 hydrogens, 1 oxygen. And if we break the bond between one of these hydrogens and the oxygen, we'll end up with a hydrogen. And then what's left is the OH. Okay? Now, when we do that, the hydrogen has a charge, a positive charge, because it's just a proton. Now, we can call this a hydrogen ion, or we can call it a proton. I'm mostly going to call it a hydrogen ion. When it disassociates, this hydrogen leaves its electron behind with these guys. That's why it's got 1 positive charge. So if it's left its electron behind with these, what's the charge on this ion? Negative. 1 negative, because it's got 1 extra electron. And we call this a hydroxyl group. Okay, that's a hydroxyl group or a hydroxide ion. It's got a negative charge and this has a positive charge. Simply because when the water molecule disassociated, when this hydrogen pulled away, it left its electron behind and that gives it a negative charge. And because it's got 1 electron down, and all it is a proton anyway, then it's got 1 positive charge. Okay? All right, so this is what actually happens. See those 2 water molecules that are hydrogen bonded to each other? Yeah? They break apart like this. One of the water molecules keeps the hydrogen, and that's actually called a hydronium ion. And then we have a hydroxide ion that results. Now, that's what happens. We're going to keep it simple. We're not going to talk about it in terms of hydronium ions. I'm just going to talk about it in terms of hydrogen ions and hydroxide ions. Everyone okay with that? Okay. So that's an accurate picture of what happens. We're going to keep it simple, okay? We're going to say that a water molecule disassociates into a hydrogen ion and a hydroxide ion. Hydrogen ion is 1 positive charge, the hydroxide ion is a negative charge. There's our hydrogen ion, there's our hydroxide ion. Now this is reversible. In other words, the water molecule can disassociate and these can rejoin and form a water molecule. And it happens very, very quickly. They dissociate, come back, dissociate, come back, dissociate, come back.
What's the purpose?
I wouldn't say there's a purpose, but it's something that occurs. So now we've got to look at the consequences of that happening.
Does it happen because of like temperature or?
It happens just because, well, it happens, the cause of it is, if I go back, it happens because of the hydrogen bonding to some degree. All right, it just says, gotcha. Yep. Sometimes the hydrogen is released from the water molecule, yeah, and it joins to the other water molecule, forming that hydronium ion. But then it very quickly can snap back. Okay? But there's many of them doing it very quickly. Does that make sense? So now we've got to look at the consequences of that. So in any sample of water, anytime we've got water now, we've got obviously loads of water molecules, but we've also got some hydrogen ions and some hydroxide ions. Okay? So now we've got to look at what that means. Everybody okay so far then? Comfortable? All right. Now, in any sample of pure water, there's an equal ratio of hydrogen ions to hydroxide ions. Right? Because if one water molecule dissociates into one of these and one of these, what must be the ratio of hydrogen ions to hydroxide ions if they dissociate and they're equal? It's got to be a 1-to-1, right? Yep. That means in a sample of pure water that the concentration of hydrogen ions is exactly the same as the concentration of hydroxide ions. Is everyone okay with that? Let's just say that in a litre of water, I had 10 water molecules, just 10, that disassociated. My concentration of these would be 10 per litre, and my concentration of these would be 10 per litre. Good? They're in a 1-to-1 ratio and they're equal in pure water at 25 degrees Celsius. Okay? All right. Everybody okay with the equal ratio and therefore an equal concentration? Okay. So, we can get a beaker of water, we can look inside that beaker of water, and we find, if it's pure water at 25 degrees Celsius, that we've got an equal number of hydroxide ions to hydrogen ions. Look, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay? Good? All right. So, at 25 degrees Celsius, in any aqueous solution, the concentration of hydrogen ions plus the concentration of hydroxide ions equals 10 to the negative 14. Now, in pure water, the concentration of hydrogen ions is 10 to the negative 7. Which means that the concentration of hydroxide ions must also be 10 to the negative 7. If we add them up, we get a concentration of 10 to the negative 14. Good?
So they're the same.
In pure water they are.
But
So
in any aqueous solution as well.
let me go back. That is true in any aqueous solution. One plus the other must equal 10 to the negative 14. Okay?
Aqueous solution, anything that.
Oh, so you're saying that, like, if you were to find...
Hang on.
Sorry.
It's all right.
Sorry.
An aqueous solution is a solution where water's the solvent. Okay? So in any aqueous solution, if you add up the concentration of hydrogen ions and the concentration of hydroxide ions, add them together, it always equals 10 to the negative 14. That's what it equals.
And then in pure water, it adds up to negative 14.
So in pure water it adds up to negative 14, but in pure water I'm going to tell you what the concentrations are. the concentration of hydrogen ions in pure water is 10 to the negative 7. Okay? Now we know that when you add them together, it must be 10 to the negative 14. Okay? So the concentration in pure water is 10 to the negative 7. That's just what the value is. Yeah? So that means the value of the hydroxide ion must be 10 to the negative 7 because it's equal, and they must add up to 10 to the negative 14. Good?
So wouldn't that be the same for the aqueous solution too then? If we knew it's 14, then
We know it's 14 for the aqueous solution. When this concentration equals 10 to the negative 7, this one also equals 10 to the negative 7.
what's the difference they could equal?
I'll give you that in the next example. I'll show you in the next one. It's a good question, but I'm going to answer it.
Where do you get negative 14 from?
Because what is negative 7 plus negative 7? Okay? That's where it comes from. Isn't it? Negative 7 plus negative 7?
Yes. But you
Yeah.
said it has to be negative 14 every time. Where does negative 14 come
Ah, so you're saying where does the negative 7 come from?
Yeah.
It just happens to be in pure water, right? When they dissociate at 25 degrees Celsius, the concentration of hydrogen ions is 10 to the negative 7. That is its value.
And the same thing goes for 10 to the negative 14 as well, right? So
They add up to be 10 to the negative 14. Yep, that's just what the values are. It's a bit like the boiling point of water is 100 degrees Celsius because that's what the value is. The freezing point of water is 0. So when water dissociates, it's just the characteristics of water, the concentration of hydroxide ions is 10 to the negative 7. And in pure water, we have the same number of hydroxide ions, which is 10 to the negative 7. Okay, we add them up, and that gives us 10 to the negative 14. But when you add the two concentrations up, they always equal 10 to the negative 14. Is everyone okay with that? There's nothing magical. It's just that's what water is. They're the properties of water. Okay? All right. Everybody okay so far? Yep. Okay. So, that equal ratio of hydroxide ions to hydrogen ions can easily be changed by the presence of other substances. So far I've said pure water. That's water and water only, no solutes. Other substances can change that ratio. Some substances, when they dissolve in water, will increase the hydrogen ion concentration and therefore decrease the hydroxide ion concentration. Those are substances that we call acids. So acids increase the hydrogen ion concentration and decrease the hydroxide ion concentration. Conversely, some substances decrease the hydrogen ion concentration and increase the hydroxide ion concentration. Those are substances that we call bases. Is everybody comfortable with me using square brackets to indicate concentration of? Yep. When I put square brackets around something, what I mean is the concentration of that substance. How much of it per litre? Okay? All right. So, in pure water, this we know is true, don't we? The concentration of hydroxide ions at 25 degrees Celsius is 10 to the negative 7. The concentration of hydrogen ions is also 10 to the negative 7. Let's add them up and we get 10 to the negative 14. So in an acid, what's the concentration of hydrogen ions? What must it be between? Between what? In an acid, the concentration. Remember,
Like a pH level type thing.
an acid will increase the concentration of hydrogen
So,
ions.
-8 to -14.
That's it. So we're not at pH scale yet.
So that's where.
We're just talking about concentration of the ions. All right? If we increase the hydrogen ion concentration, what would it be?
Between 7 and 6.
No, it'd be between 0 and 6. -1 to 6.
Would it be -1 to 6 or -1 to... In a base, the hydroxide ion concentration would be between what? He's stumped. What's the concentration of hydrogen ions in pure water? Good, 10 to -7. Okay. Now, if I add a substance to pure water, I can increase the hydrogen ion concentration. I can increase it.
Would it go up to, it would go up to -6 because, because like on the number scale, if you're going to -6, it's technically going up, but would you be down?
If I increase the hydrogen ion concentration, am I greater than or less than 10 to the -7?
I'd say greater.
Greater than?
I would, yeah, that's what I would say.
Okay. If I decrease the hydrogen ion concentration,
Then it would be less than. Okay, so then, like what I said before.
okay? Is everyone okay with that? Yep. Acids are substances that are going to increase the hydrogen ion concentration. Bases are substances that are going to decrease the hydrogen ion concentration or increase the hydroxide ion concentration. We always tend to talk about acids in terms of hydrogen ion concentration, increasing it or decreasing it. Okay? Good? So let me give you this example then. If we add to water a substance that will increase the hydrogen ion concentration, we get an acid. Yep, we're all okay with that. So for example, if we add hydrogen chloride, and that's a colourless gas, which is very soluble in water, we can bubble it through water and it dissolves. It dissolves to form hydrogen ions and chloride ions. Okay? Good. This splits up to form hydrogen ions and chloride ions. Well, by dissolving hydrogen chloride gas into pure water, we've just added a whole bunch of hydrogen ions, right? So now we've turned that pure water into an acid because we've increased the hydrogen ion concentration. And the substance we've formed is hydrochloric acid. Okay? So the resulting hydrogen ion concentration is 10 to the -2. All right? When we do that, that's just what the value is. So if this represents our hydrogen ion concentration, yep, this is our hydroxide ion concentration, and we know they always add up to 10 to the -14. What must be our hydroxide ion concentration? Good, -12. Okay.
So it's still called hydroxide even though it's chlorine? It's still called hydroxide because even if it's chlorine?
We've always got, that's just, well, I'll leave that out. Actually, I don't need to draw that. We've always got these. They're always present because water's disassociated. Okay? When we add hydrogen chloride to water, we just add a whole bunch of these and a whole bunch of these. And we've always got hydrogen ions and hydroxide ions because it's water.
So where is that in the equation? Because it used to be in the
This is just the hydrogen ion concentration for a solution with hydrogen chloride in it.
So you're saying the concentration of hydrogen hydrochloric acid is at a -2.
Yeah.
So both of those, the H and the CO.
Here we've got H2O, and we're going to add HCl. Okay? So we've got hydrogen ions, we've got hydroxide ions, and we've got chloride ions. Before we added this, we had equal ratios, equal amounts of these, an equal ratio, yep? But then what we did is we dumped in a whole bunch of these and a whole bunch of these. That means we've now got many more of these than we have of these. Okay? So this is just an example of one substance that when we add it to water increases the hydrogen ion concentration and it results in an acid. Good? Yep.
So the 10 to the -12 is not the chlorine, it's still the
It's the hydroxide.
Oh, okay.
Yep. Yep.
Oh, okay.
If we added the hydrogen chloride, this is what happens to the ratios of hydrogen ions and hydroxide ions. So in pure water, they're 10 to the -7 each. But we've just added a whole bunch of these, and that shifts the balance. Okay? Yeah.
You may have said this, but how did you get 10 to the -2?
That just happens to be the value.
Oh, that's just a given number.
It's what happens when you put hydrogen chloride into water at 25 degrees Celsius.
Okay.
Yeah. It's the characteristics of that, of hydrogen chloride. I could put a different acid in there. For example, acetic acid. And I think it gives a value of about pH 4. So the hydrogen ion concentrations tend to the -4. It just depends on what the acid is. Okay? Okay? I'll come back to this because I don't think we're going to finish in the time we've got, but I just wanted to share this with you. Okay? So I think this helps sort of put it in perspective a little bit. We've got hydrogen and hydroxide ion concentrations which are equal. Okay? And then we've got substances that are acids, and that's when we've got a greater hydrogen ion concentration than hydroxide ion. Now, hydrochloric acid, the one that I showed you, is at about this value here on this scale. It's very acidic. But there are other acids in tomato juice and beer and black coffee and rainwater, which give different hydrogen ion values. Some of them might give it 10 to the -5, for example. It just depends on the acid. And then we've got substances which are quite basic. Okay, in this case, we've got a lot more hydroxide ions than hydrogen ions. So, for example, I can take oven cleaner, which is sodium hypochlorite. And what that does is it dumps a whole bunch of hydroxide ions. It adds loads of these. So now we've got a very high concentration of these and a much lower concentration of these, and that gives us a base. Okay? All right. Okay, so test on Thursday.